Okay, we're continuing on here with the solutions chapter. So we were talking about solutions and we were talking about really concentrations last time and concentration units. So we talked about a few different types of percent concentrations. We had our percent mass to mass, which again is our mass of the solute over the mass of the solution times 100%. We also talked about percent volume to volume, volume of solute over volume of solution times 100%. We also had percent mass to volume, which is our mass of our solute over volume of solution times 100%. Again, remember that if you are given sort of the percentage of each of these things, you can't convert them into a usable conversion factor. So if we had a 225% by mass sodium chloride solution, that would mean you had 2.25 grams of sodium chloride in 100 grams of solution. Or again, you can flip it around, 100 grams of solution. You would have 2.25 grams of sodium chloride. You could also obviously do that for any of the other ones as well. Typically, this guy is milliliters over milliliters. So you would assume something like 2.25 milliliters of sodium chloride in 100 milliliters of solution. This one's usually grams per milliliter. So you would do something like 2.25 grams of sodium chloride in 100 milliliters of solution. The other important thing we talked about, right, is that the bottom here, especially with that one, our percent mass to mass, you want to make sure, again, that you get the actual mass of the solution, not just a solvent, as it is very commonly given to you separate from each other. Thank you. The next type of concentration we talked about, which is really probably the main one we use most of the time, is molarity, which is capital M, and that equals moles really of solute over liters of solution. That's really moles of solute, liters of solution. But we do think of it like in the formula. Molarity is moles per liter. That means we could solve for any of these sort of units. Liters is moles per molarity, or divided by molarity, and moles, which is a common use of it, liters times molarity. Again, always need to make sure volume is in liters when you're dealing with molarity by itself in this sort of formula. Otherwise, again, you'll be off by a factor of 1,000. Remember, 1,000 milliliters in 1 liter is a common conversion that's used a lot. Also, to get to moles of the solute, using the molar mass to go from grams to moles is used a lot in these type of problems. We could calculate the molarity. When you're doing calculations, once again, as we talked about, you may want to take more of a dimensional analysis approach to it and really get rid of the big M when you're doing a calculation. Again, it's very, very common. People, for some reason, think of the big M as like just being moles because they just see the M and they forget all about the liters part of it or where the volume is. So, you know, you can convert this into a usable conversion factor like 2.25 moles of sodium chloride in a liter of solution, or you could flip it around, liters up on top, 2.25 moles of sodium chloride on the bottom. It's always per 1 liter, and the number always stays with the moles part. And again, you can take more dimensional analysis approach, which sometimes is the better move because you can see both units, and hopefully you won't forget about the volume part of it. Any questions on that there? All right, so we skipped a couple of examples, or maybe an example there, and did one before. So let's go back to that example that maybe we passed over. So why don't you give this a try for each of these solutions. So there's 2 separate solutions. So this guy and this guy, do them separately. So for each of the individual solutions there, we want to know what is the concentration of the actual ion. Okay, let's take a look. So remember, in terms of concentration, from sort of an ionic compound to each of the ions that are in solution, which in most cases, that is pretty much what's floating around there is really the ions because they're strong electrolytes. So they're not going to stay together. You want to think about how it breaks apart. So if we look at the first one, which is sodium sulfate, in solution there is going to break apart into 2 sodium ions and a sulfate ion. Which means if the concentration of the whole thing is 1.2 molar, you could really do like a stoichiometry sort of relationship. It is a 1 to 2 relationship, which means in terms of the sodium ions that are present, we would actually multiply the concentration by 2, and that would get us 2.4 molar as the concentration of the sodium ions that are present. In terms of the sulfate, it is a 1 to 1 relationship, which means basically we're just going to multiply the concentration by 1, which will keep it the same, obviously, in this case. As we talked about, I think last time, obviously, they're not additive. They don't add up to the total molarity. They are sort of the proportion. So basically, for every one of these units that go for a swim, you get twice as much sodium ions floating around as you do sulfate. So the concentration of sodium ions in that solution is twice the amount of the sulfate in this particular case. That, once again, is sort of the short approach there to that calculation. Once again, the longer, more stoichiometry approach is 1.2 moles of the entire thing here per liter. Using our stoichiometry, 1 mole of the whole thing gives us 2 moles of the sodium ions. Moles of the whole thing cancel, and that gives us our 2.4 moles of sodium ions per liter, which is how we get to this number here. That's sort of the long version of it. Short version is multiply by 2, which is the stoichiometry part of it, and it'll give you the right concentration. Any questions on that there? Obviously, we did for the sulfate, the part in the middle would be a 1 to 1 relationship, which is why, again, we multiply it by 1 in that case. Taking a look at the other one there, which is 0.75 molar K2CrO4. Once again, when this breaks apart, we will get a couple of potassium ions and 1 chromate ion here. And again, we got 0.75 molar for the whole thing. It is a 1 to 2 relationship here for our potassium. So in this case, we would multiply the potassium by 2 to get the proper concentration. And that will give us 1.5 molar for the potassium. And again, it is a 1 to 1 relationship between the other guy there, the chromate, which means we're really going to just multiply it by 1 or keep it the same in this case. 0.75 molar. Any questions on, again, how to relate the concentration of the whole thing in an ionic compound to its ions? That's probably the easiest way. Again, if it broke apart into a 1 to 3 relationship, you would multiply by 3 and so forth, basically, is how you would do it. Any questions on that there? All right, so let's take a look at one here. How many moles of sodium ions are present in 42 milliliters of 0.3 molar sodium chloride? So take a few minutes, see what you come up with. Things here, we are looking for the molarity of just the sodium ions that are present in the solution. We do have the molarity of the entire thing, which is 0.35 molar. We do have the volume here, which is 42 milliliters. So again, if you're not sure, we can think about molarity, which is moles per liter, and clearly I have the molarity. I don't have the in liters, but I do have the volume. So we can get to moles. So there's a couple ways you could do it. You could either kind of use the sodium chloride and then get to the sodium ions, or you could just straight up get the sodium ions from this. So as we just talked about, we will know hopefully that sodium chloride will break apart into a sodium ion and a chloride ion, which means that if this guy is 0.35 molar, it is a 1 to 1 relationship between those two, which means this guy will also be 0.35 molar. And for reference sake, this guy, the chloride, would also be 0.35 molar. Not that we need it in this particular problem, because we're just looking at the sodium here. Again, that basically means that the sodium ions has a concentration of 0.35 moles of sodium ions per liter. So now that we have the molarity of the sodium ions by itself, we really could rearrange this and solve for moles. Moles will equal liters times molarity. Again, a really important thing, got to have it in liters here. So we want to do our 1,000 milliliters is a liter, going to give us 0.042 liters. So taking this here, 0.042 liters times the molarity of just the sodium ions, 0.5 moles per liter of sodium. Liters will cancel. We'll end up with here 0.0147 moles of sodium ions. Any questions on any of those steps there? You could have also figured out the moles of sodium chloride and then did basically a mole to mole relationship and converted it into sodium at the end ions. Any questions on that there? In this case, obviously, if we did the chloride, it would come out the same, basically, yeah, because it also is a one-to-one relationship. Question on molarity. I think the other day we calculated how many grams and stuff that we needed. We're going to make a solution. All right, the next thing we're going to talk about then is a dilution. And in a dilution, we oftentimes will dilute more concentrated solutions, which are sometimes referred to as stock solutions, to make them less concentrated. So a dilute solution will have less solute dissolved in it per volume of solution. And really the only thing that we kind of do to a solution when we do a dilution is basically add more solvent. And in a lot of cases that solvent's water. So a lot of times when we do a dilution, all we're doing is adding more water to it. And that will lower the molarity of that solution. The reason it will lower the molarity of the solution is, again, molarity is our moles of solute over liters of solution. So when we add more solvent, that is basically increasing the bottom part here. And obviously when the bottom part gets increased, the molarity will then come down as you're dividing by a larger number and the molarity comes down. So the thing that it really doesn't change is actually the solute in that solution. So however much solute you have floating around in there is what you have floating around in there. But the concentration will change because you basically dilute it down, say, with a lot more water. So the moles of solute before the dilution and after the dilution will be the same. It's just the solvent that you're adding to basically lower the molarity in a lot of cases. So there actually is a formula that we use for dilutions, and this is typically the one that most people use, which is M1V1 equals M2V2. And this is the dilution equation. And typically the M1s is the more concentrated solution. Doesn't necessarily have to be, but usually it's the more concentrated. And the 2s there are the more dilute solutions. M1 is the molarity of the more concentrated solution. V1 is the volume of the more concentrated solution you're going to use to make the solution. M2 is the molarity of the more dilute solution that you want to make in a lot of cases. And V2 is the total volume of a diluted solution that you want to make in those cases. In this case, this is the one place where if you want to, you do not need to convert volume into liters, and you can leave it in milliliters if you're specifically using this equation only. If you're using molarity by itself, you need to convert it to liters. Otherwise, you'll be off by a factor of 1,000. But in this case, you can actually leave it. The reason you could leave it in milliliters is if we just look at units, and let's just say we were solving for V2, V2 would be M1 V1 divided by M2. And if you did that, molarity, milliliters, molarity will leave you with milliliters when it's all said and done. So that works out okay in this particular equation. Also, if we say solve for M2, that would be M1 V1 over V2. And if you did it milliliters, molarity times milliliters divided by milliliters, milliliters would cancel, leaves you with molarity. So it does work out okay. This is the one place, again, you can leave it in milliliters as long as it's obviously milliliters on both sides, or if it's milliliters on one side and you're solving for volume, you will get in milliliters. The real reason is because when you take milliliters, again, times molarity, which I think we might have talked about, you actually get millimoles, not moles. And if you divide it by milliliters like you would in this particular case, the millis cancel and leaves you moles per liter, which gets you back to molarity. So it does work out okay. But sometimes people mess up because when they're using not this equation, but just molarity by themselves, they multiply by milliliters and you'll be off by a factor of 1,000. So by itself, molarity and volume need to be liters, but one place you can leave it in milliliters is here. Any questions on that? There is a more generic version of this equation that sometimes people will use or textbook will use, and it is just generically C1V1 equals C2V2, and C just stands for concentration here. Although in most cases, the concentration we're going to use is molarity, it doesn't always have to be molarity. So you can technically use this equation for any type of concentration like percent mass to volume. You can put those guys in there and do it as well. So sometimes people use C1V1 equals C2V2. I personally roll with this one because it is what's used most of the time, but you can definitely use some other concentration unit instead of molarity in those cases. All right, so let's take a look at one here. What volume of 19 molar sodium hydroxide is needed to make 1 liter of 0.15 molar sodium hydroxide? Okay, let's take a look at this one. So we basically have a bottle here of 19 molar hydrochloric acid. We want to take some of that solution and put it into this new bottle that will be a total volume of 1 liter or 1,000 milliliters. And hopefully at the end, it will have a concentration of 0.15 molar. So we could use our M1 V1 equals M2 V2 here. Once again, this is usually the more concentrated side, and this is the more dilute side. So in this case, we do have our more concentrated molarity. We do not have how much we're going to use of it. M2 is what we want to end up with, which is 0.15 molar, and we want to end up with a final volume of 1 liter. We're going to send this guy to the other side there, and that will give us a V1 of 0.0079 liters, or about 7.9 milliliters of this case of our 19 molar. Yeah. You could leave it in either way. In this case, you could leave it in liters as the original one was liters. I converted to milliliters just so we don't have so many zeros, and what we're going to talk about in just a second here, but you could leave it in liters, is fine. Yeah. Other questions? So what that really represents is what we would want to do is take out from this 19 molar bottle, which is more concentrated. Again, I'm just going to use the milliliters here, 7.9 milliliters of our sodium hydroxide solution, right? And would I then add 1,000 milliliters of water in this case? The answer is no, because if I added 1,000 milliliters of water, I would end up with 1,007.9 milliliters, which is over a liter, right? Which is what we want to end up with. So a lot of times in these problems, we oftentimes are asked, how much water should we add? And usually that is your final kind of V2 minus V1. So if we did that, we want to end up at 1,000 milliliters, which is 1 liter, minus 7.9 milliliters we already put in there. So we need something around 992.1 milliliters of water to put in there. So we would do this with 992.1 milliliters of water. That will give us a total volume of 1 liter. We would then obviously mix it up really good, and we then should have a solution that has a concentration of 0.15 molar. So again, a lot of times in these dilution problems, they sometimes will ask you, how to make it or how much water you need to put in there. So you want to make sure, again, you read them carefully. Any questions on that there? All right. So let's take a look at one, maybe like that. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar? We got a more concentrated 5 molar bottle sitting there. We want to eventually make a badly drawn bottle that's 500 milliliters. And again, ends up with a concentration of 0.25 molar. It's obviously calcium nitrate to calcium nitrate, no reaction or anything happening here. So we'll do our M1 V1 equals M2 V2. In this case, we do have our M1, which is our more concentrated. We do not have V1. Our M2 is 0.25 molar. And in this case, again, as I mentioned earlier, if you want to convert it to liters, you can, but it is okay to leave it in milliliters in this equation. It just means that when we solve for volume here, we will end up with milliliters at the end. So V1 will equal 0.25 molar, or 500 milliliters divided by 5 molar. And once again, this is why it works out. Molarity will cancel on both of those. It will leave us with milliliters. So again, we just end up with milliliters here. And that's going to be I believe 25 milliliters, if I'm not mistaken. Yeah. That 25 milliliters is the amount of the more concentrated guy that we want to put in there. But really the question is how much water we want. So we do need to get the difference right. Here again, we would not want to put 500 milliliters of water because we will end up with a volume of 525, which will not give us that molarity we're looking for. So again, the volume of water would be our V2 minus V1. And that's going to be 500 milliliters minus 25. Going to need about 475 milliliters of water to go with it. So 475 milliliters of water gives us a grand total of 500. Again, give it a shake, or maybe not so much a shake, maybe a mix would be good. And we will end up with 0.25 molar solution. Question on that one there. So again, make sure on these you're careful because sometimes they will ask, obviously like this one, the volume of water. And sometimes they'll ask how much of the more concentrated solution. Maybe they want to know the concentration of your new solution as well. So you can solve for really any of those. M1, V1, M2, V2s could all be solved for in these type of problems. Any questions on dilution here? Okay, next thing we're going to talk about then is everybody's favorite, which is stoichiometry involving solutions. So once again, the good news is stoichiometry problems, much like what we saw with gases, pretty much works the same way as normal stoichiometry problems. There still really is those same steps. You want to make sure you have a balanced equation. You want to convert to moles. You want to basically do the mole relationship from the equation. And then you want to convert to some other unit at the end. Just like in a normal sort of situation, you also want to make sure that if you have a limiting reagent sort of situation, that you calculate the limiting reagent. You do have to do some type of calculation to determine which one is the limiting reagent. You can't just randomly pick one and go, oh, this one looks right. Yeah, so you do have to do that. You still have to do it in solution stoichiometry as well. The difference is in a couple places, a lot of times in solution stoichiometry is how we kind of get to moles. So we can still do our grams to moles using molar mass from the periodic table, but sometimes we may use liters and molarity to get to moles. So that's a very common sort of calculation. And on the back end as well, we also could still do moles to grams if the question asks for that, like we've done before. But on the back end of these calculations, sometimes we will also use the molarity sort of equation. So you might actually be calculating the molarity using the moles from the stoichiometry part to sort of get the moles part of it. Liters would probably be given to you and you can calculate the molarity. The other thing that you might do is look at a volume if you are given the molarity. So that's another sort of situation. Once again, you get the moles from the stoichiometry part. So the ending also, again, could be just like a traditional stoichiometry problem, moles to grams using the molar mass. So, you know, there's a few different options that you could do in solution stoichiometry. But a lot of times, somewhere along the way, there's some type of molarity and volume sort of incorporated into the calculation. Any questions on that there? So let's take a look at one here and kind of see some of these steps. We want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.2 molar barium nitrate solution to precipitate all the barium ions as barium sulfate. We also want to calculate the mass of the barium sulfate that's going to be formed. So we're actually going to do, just to start with, the first part here. So from this part back, we'll do. So obviously here we have everything in words. So we definitely want to turn it into formulas and equations. So we want to calculate the mass of solid sodium sulfate that must be added. So that's a reactant. So again, based on your knowledge, that should be sodium sulfate there. That needs to react with barium nitrate, barium +2, nitrate -1, should give you something like this. When you see something like this, based on your knowledge, you should know that this is a double displacement reaction, right? Which would make a precipitate. So again, in a double displacement reaction, we're going to switch partners. Also remember that when we write it, we want to make sure we get the correct formulas first. So sodium is +1, nitrate is -1, which means it gives you this, NaNO3. Barium is +2, sulfate is -2, which means when you put that together properly, that is what you get there, which is barium sulfate. You want to make sure you, again, correct formulas. Now that you have the correct formulas, we can balance them. So we do need to put it some, maybe a 2 there. And I think that might be it, actually. That will balance the equation. Any questions on that there? So now that we have our equation balanced, we want to do step number 2, which is take whatever they gave us and convert it to moles. So really the only thing that was given to us is we have 250 milliliters of 0.2 molar barium nitrate. That means from that we can get moles, which is what we're looking for. Remember that, again, molarity is moles per liter. So moles here would be liters times molarity. And this, again, is an important spot where we do need to convert it to liters. So we want to make sure we convert that 250 milliliters into liters. So if you take 250 milliliters, again, 1,000 milliliters is a liter, 0.2500 liters. 0.2500 liters. We're going to use our molarity here. We're going to get rid of the big M and convert it to moles per liter of barium nitrate. Liters will cancel. This gives us 0.25 times 0.2. Going to give us 0.05 moles of barium nitrate. First off, any questions on that? Is this a limiting reagent problem, by the way? This is not a limiting reagent problem because we only have enough information to get the moles of one reactant, right? So when you have enough information to get the moles of both reactants, then it is a limiting reagent problem, and you need to do that additional step to figure out which one's the limiting reagent. But in this case, it really is just a basic stoichiometry problem, which means we're halfway to our end here. We have balanced the equation. We have converted to moles. We are now going to do the mole to mole relationship. In this case, for the first part of the question, we are interested in how much sodium sulfate we need. So we're interested in the mole to mole relationship between those two from the equation. And as we could see from the equation, it is a 1-to-1 relationship. So for every 1 mole of sodium sulfate, you get 1 mole of barium nitrate. So that makes the math not too bad. So that is what we'll do next, which is the third step. 1 mole of barium nitrate, which is the stoichiometry part, gives us 1 mole of the sodium sulfate. Moles of the barium nitrate will cancel. I think I could do that math still. 0.5 moles of sodium sulfate. At this point, we're looking for our fourth step, which is to convert to the units we're looking for. So in this case, we actually do want grams. So we're going to take moles to grams like we've done before. And to do that, we would have to go to the periodic table and remember that we do need the molar mass of sodium sulfate here. So sodium sulfate would be 2 times 2299 for the sodium, plus 3207 for the sulfur, plus 4 times 16 for the oxygen. And that's going to give us about 142.1 grams per mole. So we'll do our last step here, which is to figure out how many grams we would have to put in there with it. Using our molar mass from the periodic table, 142.1 grams per mole, grams up on top. So we end up with grams, moles cancel. Looks like about 7.1 grams of sodium sulfate would be needed in this case. So this really is just a basic stoichiometry problem. Again, in this case, we actually only use molarity up front, but same 4 steps: balance equation, convert to moles, mole to mole relationship, and moles is some other unit here. Any questions on that there? All right, then once you do the second part, which is we also want to know how many grams of barium sulfate should be formed. So why don't you give that a go and give you some numbers that might be helpful. Obviously using the same equation. Barium is looks like 137.3. Sulfur 3207. And oxygen 16. All right, so take a moment and see how much product we would actually make in this case. There's a few different ways you could do it. So really at this point, you're just kind of picking up halfway through. We could start our same steps. We obviously already still have the same balance equation from before. We obviously as well already got into moles from our previous problem. So you really could pick up from that point. We have really 0.0, we got there, 5 moles of barium nitrate. And again, that's just the first 2 steps that we did previously. By the way, you could have also just picked up from that guy as well and started with those moles, whichever one you want to do, it will all come out the same. In this case, I'm going to stick with the barium nitrate, and that means the next thing I want is the mole to mole relationship between now the barium nitrate and the barium sulfate, which in this case is a 1-to-1 relationship as well. That makes it nice. So doing our third step here, since our first 2 was kind of already done for us, we will do 1 mole of barium nitrate from the equation will give us 1 mole of barium sulfate. That obviously again will give us 0.05 moles of barium sulfate was produced. That would be our theoretical yield in moles, but we do want grams. So we're going to get the molar mass here of barium sulfate. So that's 137.3 grams per mole for the barium, plus 3207 for the sulfur, plus 4 times 16 for the oxygen, going to give us a molar mass here of 233.4 grams per mole. So we'll use that for our fourth step here, which is to figure out how much product we made, 233.4 grams per mole of barium sulfate. And that is going to get us, call it 11.7 grams of barium sulfate should be produced. That would be our theoretical yield in grams. Once again, as I mentioned before, you could have, if you want to, since we did in the first part, calculate that number, you could have just continued on from that number and you would end up with the same as well. Any questions on that step there? All right, so let's try a fresh problem here then. Wherever it is, there it is. All right, calculate the mass of white solid calcium carbonate that forms when 25 milliliters of 0.1 molar calcium nitrate is mixed with 20 milliliters of 0.15 molar sodium carbonate. All right, give it a go, follow the steps. Kind of getting to the end. Let's take a look at it, how you're progressing, make sure hopefully you're on the right track. So obviously we need to start with the equation. So in this case, we're going to take calcium nitrate and we're going to mix it with some sodium carbonate. Once again, you should be able to recognize this as a double displacement reaction. These two guys are going to switch partners. Once again, we want the right formula. So sodium +1, nitrate, once again, -1, going to give us just NaNO2. Calcium +2 and carbonate -2, which means when we put it together, we end up with this guy. Obviously here now we want to balance it. So a 2 there, I think once again, we'll do it in terms of the balancing. Any questions on that there? By the way, that is a solid. All right, we are given, in this case, we have 25 milliliters of 0.1 molar calcium nitrate. We also are going to mix it with 20 milliliters of 0.15 molar sodium carbonate. I am given both the volume and molarity for both of my reactants, which means I can calculate the moles of both of these reactants. That should scream to you that this is a limiting reagent problem. You could get the moles of both of the reactants. So you do need to do that limiting reagent step in this problem if you want to do it correctly. So the first thing we're going to do is convert these guys to moles. So we're going to convert both of these volumes into liters. So we're not off by a factor of 1,000. So for the calcium nitrate, that's going to give us 0.025 liters. Times the molarity, which is 0.1 moles per liter of our calcium nitrate. Going to get us 0.025 times 0.1 gives us 0.0025 moles of calcium nitrate. We're going to do the same thing for our sodium carbonate. So that's going to be 0.02 liters. Times the molarity there of our sodium carbonate, which is 0.15 moles per liter. Again, I'm using both of the units there so we can see the liters hopefully cancel. And that is going to give us 0.02 times 0.15, 0.003 moles of our sodium carbonate. So this is like our starting amounts for both of these, right? And that means we do need to do the limiting reagent calculation. You cannot make that determination, by the way, from these two values. You actually have to do a calculation to make that determination. So I'm going to choose calcium nitrate here, 0.0025 moles of calcium nitrate. And I want to use up all that calcium nitrate. So I want to see how much of the sodium carbonate I need. It is a 1-to-1 relationship from the equation. That means that I would need 0.0025 moles of sodium carbonate is needed. When I look at my sodium carbonate, I have 0.003 moles of it in comparison. So I do have enough, and it is that calculation that tells me that this is my excess reagent and this guy is my limiting reagent. So you got to do some type of calculation. Any questions on that? At this point, now that I've determined my limiting reagent is the calcium nitrate, I will then use the starting amount of my calcium nitrate, which is 0.0025 moles of my calcium nitrate. I am now going to do the mole to mole relationship between calcium nitrate and calcium carbonate. Again, it won't always be 1-to-1, but it looks like we chose some easy examples here. They got 1-to-1s. So we have 1 mole of calcium nitrate gives us 1 mole of calcium carbonate. That means that we should produce 0.0025 moles of calcium carbonate. At this point, I then want to convert it to grams because that's what I'm looking for. So I want the molar mass of calcium carbonate that I could get from the periodic table here. So that's going to be a 4008 plus a 1201 plus 3 times 16. It's going to give me 100.1 grams per mole as my molar mass. We're going to use that here to get to the grams, which would be 100.1 grams per mole of calcium carbonate. Moles cancel. Gets us about 0.25 grams of calcium carbonate would be formed, which would be the theoretical yield in this case. Basic steps, convert to moles. Need to do the limiting reagent calculation, then mole to mole relationship, and our moles to some other unit type of relationship there. Actually, convert to moles would be our second step, obviously. Here, there we go. Limiting reagent calculation was down here. There we go. That would be our third step, and this would be our fourth step. All right. Actually, that would be our fourth step. I'll get my numbering right. There you go. There's the third step. Any questions on any of that there? Clearly, at this point at the end, since we did have the moles of calcium carbonate, if we had the molarity, we could have figured out a volume. If we had something like that, if we had the volume, we could do a lot of stuff, obviously, with that fourth step. Any questions on any of that there? All right, we'll lay it up there for today.